this one little screen. It's like, if you think about it, we got 16 colors. We have essentially 2,000 pixels and 512 bytes. So we kind of have to be creative in the same way that even the old school video game programmers had to do. You have to do, like in this case, I did 8 by 8 sprites that were 4 colors each. So you can pack a lot of pixels into just one byte. In this case, like 4 pixels into each byte, and you have a program that knows how to load the sprite and place it into memory or place it on the screen and all that kind of stuff. I mean, this isn't really a huge part of the talk, this description. It's just I like looking at this slide and going into it. So this is kind of what we're going to be going over. The first stage of this talk will be about just how to do boot sector programming. It's actually, if you know assembly, it's actually super easy to get into. There's not a lot you have to set up. It's just there's no like headers like PD or ELF or anything. It's just straight machine code. And then we'll talk about debugging the code, which is a little bit harder than normal user space debugging, but it's not too bad when you attach GDB to QEMU. And then we'll showcase some demos of programs and games that other people made, that we made, and even kind of a crappy game, again, that I made that would actually make heavy use of debugging that we'll talk about, because that's some stuff you want to do just to play the game. So I'll get started with that first list of bullets there.
A show of hands, how many of you guys actually know assembly?
Cool.
I'll say majority of you.
Yeah, that's not bad. That's pretty cool. So this is just like 16-bit assembly. It's not going to be that much different than what you're used to. This is the slide for why I do it, because it's fun. I mean, in my own definition of what fun is. I also think that limitations encourage creativity. A good example of that is just a couple days ago, I actually made a boot sector that actually booted a kernel, like a really simple one, which that was just 2 days ago. Up to that point, I never actually used a boot sector for what it's supposed to be used for. And before I even did that, making these games, I kept on thinking, man, what I could do with another like 10 bytes, but just had 10 more bytes to play with. I could do all this cool stuff. And then, I learned to escape that and have more memory to put more code in. And at that point, I'm like, shit, I don't know what to do now. Just like too much possibility. So like those limitations of only having 512 bytes actually like kind of seeds the creativity. It makes you have to be creative. And then one of the afterthoughts is ring zero programming. So just to get it out of the way, because this is, after this slide, I'm not going to really talk about ring zero instructions anymore, because I don't care. I thought I cared. Like, I actually read through the whole, all 3 volumes of the Intel manuals. I guess it's 4 volumes now, but back when it was just the 3, I read those. And I kept on reading these ring zero instructions. I'm like, man, I want to try this, and then I get an error when I tried it, and I'm like, oh crap, I have to be, a different privilege level. So because I couldn't use them, they interested me more. I'm like, well, they got to be way cooler if I can't use them. But I didn't, like, I was too dumb to like get to ring zero. Like, whatever I read about it, it's like you got to like, set up a driver or make your own driver to like hook into that space. And I was like, man, that's too confusing. So I gave up for a while, but then down the road, does anybody know about proof of concept or get the fuck out? The zine? There's one guy that, yeah, okay, cool. You all know how amazing it is. The thing that inspired me was, I think it was like maybe the 2nd or 3rd issue in, this guy wrote a boot sector game called Tetranglings, which I'll demo, we'll see it here. But it was like a Tetris clone in boot sector, and I was like impressed, amazed. But then I also realized, well, this is something I could work off of. I could look at this guy's code and learn from it, and then also be in an environment where I can play around with ring zero instructions. So I got to that point. Here's most of the ring zero instructions, and I come to find out they're all kind of pretty boring. So this talk is actually not about ring zero programming. So now we'll just talk about what it takes to actually be in an environment to do boot sector programming. I recommend QEMU, but for an emulator, but you can also use VirtualBox and a lot of other stuff. But really, this is like the bare minimum. What you see in this slide here, this is kind of the bare minimum. You need to have it end with the bytes 55AA. And you see it as a data word here because it's, well, I mean, you see it in reverse because the endianness of it. But as long as the 512 byte image ends with 55AA, Everything else is your own code. There's no other overhead, which is kind of cool. And then this that first bullet, that assembly, you just put that at the end of your code to make it so it pads out the bytes to nulls, so it actually is equal to 512 bytes. And then you also want to begin, like you want this to be at the very beginning of your assembly file. It's not an actual instruction, it's kind of a directive, but being that the BIOS loads your code into 7C00 memory, every time you do like a jump or a call or whatever, it needs to know to add that as an offset for you. So it's kind of doing work for you. If you don't do that, you'll kind of go insane for why your programs aren't working. I think we've both had that issue. I forgot this. I know you have too, because I reminded you one time.
I wanted to point out,
Yes.
is the stuff you were showing before, is that NASM specific?
Yeah.
Okay.
Yeah.
Just, I don't know if you mentioned
It's a
that.
good point. Like that stuff is NASM specific. It's just my favorite assembler. I mean, you're probably going to have to use similar things like that with other assemblers if you use it, and it's probably not going to be that much different syntax-wise. So, and this slide right here, speaking of NASM, is the NASM instruction I'd run. So it's NASM and then your boot file, so I just call it yourboot.asm, and then -f bin for a binary, like the format of it, and then -o yourboot.bin. If you don't do that, I think it might just automatically create a file for you, but I do -o just to take control and make the file name. And then to run it with QEMU, which is what I recommend, but you can do it with other stuff too. It depends. On some systems, you type QEMU after you install it, and then just your binary file and it loads it. But on some systems, like actually on this OS X system I'm on right now, I actually have to run QEMU-system-i386 and then -hda and then my boot file. So one of the other should work for you. And that's QEMU. But if you wanted to do VirtualBox, I thought it was a little bit different, but I'll show you what I thought that you had to do to get it to work. Really, it's just different padding. And I think, I don't know, the file extension thing, I don't know if that's still required too, but I'm going to let him speak to this real quick, because I do this works, but apparently you don't have to do all of this to get to it to work.
Yeah, so the stuff that we did before, just to get it to work in QEMU, has been working fine for me, so it might be Mac.
No, I mean, mostly I did this in Linux, but...
Okay. I don't know, but this part wasn't necessary in some of the testings that I did.
So ignore this slide. Did you have to do did the file extension matter at all for you?
I always just did data image for QEMU and VirtualBox.
Okay.
And do nothing.
Okay. So again, setting up our environment. This is funny enough. This is optional, but being that you're not in user space, you don't have the stack set up for you. You actually have to do this manually too. If you want to use a stack, you have to set up where the stack is. But I mean, it's funny that I say it's optional because like the stack really isn't required. If you don't want to do calls or like pop and push and those kind of instructions or returning or whatever stuff that depends on the stack. If you're not doing those, which I mean we do, so I would set up the stack. But I'm just saying it's kind of cool that you're in such a stripped down environment. You don't even need to use a stack if you don't want to use a stack. But this is a way that I recommend setting it up. Setting up the stack, and I just load it into memory at 9C00, which is like 200 hex, but 512 bytes after the boot sector itself is where we put the stack space. And then there's a couple ways to do video. First, I'll talk about the preferred way that I like to do it, and then he'll talk about the way he does it, which is actually kind of cooler than my way. But the way I do it is just a text mode, so it's like 80 by 25 characters. This is a code that should get that running for you. I put the video memory at like the address of B800. It's not required to put it there, that's just where I put it. And then you do an int10, which is a BIOS call with 3 and AL as the argument to do text mode. And you call it, and you have a video mode set up. But there's other things about when you're in that environment that you need to know. First of all, I mean, it's like I said, it's 80 by 25, but each pixel or element on the screen is 2 bytes of data. So you have 4 bits for the background color, 4 bits for the text color, and then another 8 bits for the character itself that you want to put on screen. And that's not actually ASCII though, it's code 437. It's really similar to ASCII. It's kind of actually better in this environment because you get a lot of cool characters and shit that you can use for your games. So that's that part of it. And as far as the colors go, they're in order. So like for that nibble, the 4 bits for the background and also for the foreground, like, you know, 0, 0 is gonna, or I guess 0, 0, 0, 0 is gonna be black, and then 1 is blue, and you know, so on like that. That's the order of the colors that is shown up here. Because I wouldn't even really remember this, I made myself a table that is also boot sector. Like this is actually a program that displayed this chart. But this is like all the different combinations of background and foreground colors in hex, and it's actually representing the real background and foreground color it is in this slide. So like if we look at say 5-7, you know, that's a purple background color represented by the 5, and a gray foreground color represented by the 7. So you'll notice anything that ends with 7 in that row is all light gray for the foreground. I mean, it kind of makes sense. But I mean, sometimes it's hard to visualize, so I just made this program as a tool for myself. And then now Brian's going to talk about graphic mode setup, which is similar, but yeah, different.
So for graphic mode, you're not working with characters anymore, you're actually working with pixels, and I like this mode better. I'm going to do a demo later with the snake game that I created in this mode. For graphic mode, it's pretty much identical, except for the memory location that the ES register is pointing to is different from the 03 text mode that Eric uses, and then you just need to specify the 0x13 for graphic mode, and then everything else is just the same. For graphic mode, you get a 320 by 200 pixel canvas to work with. Each pixel is 1 byte, so all of the bytes are sequential. So if you want to move on the x-axis, you can just move that way. But if you wanted to move on the y-axis, you would just multiply your x-axis by 320. So you can actually just get like an x, y, z coordinate.
Text mode similar.
Yeah. Right. And then so obviously because it's 1 byte, you get 256 colors. And so this is kind of a palette of what those colors are, and I think it has more colors than text mode.
Oh yeah, a lot more, because as you saw, there's only 16 colors for text mode, so this is significantly more colors. So now we'll talk about important registers, because you might be thinking, like, how do I get these pixels or characters on the screen? The big thing is, in the way we implemented this is we have video memory, like in its own location, and the DI we're using as a register to point to that video memory. So we load our pixel or character data into DI, and then we do the STOSW or STSV, sometimes, but I do W for word size because it's 2 bytes in the case of text mode. And that'll just put it into video memory. It's actually, if you look at the code, it's a lot simpler than it sounds. And then the AX register is where I tend to put the pixel data before doing the S2SW. So I should say, I might have misspoke. DI is the location on the screen of where that pixel goes. The AX register will be the pixel data, and AX being a 2-byte register. So you have the 2 nibbles for your colors and then the last byte for your character. So before doing the STOSW instruction, you just put into DI where you want it, and AX what you want it to be, and you do the S2SW, and it puts it on the screen, and that's it. And then the CX register, I mean, in this case, we use it kind of how a lot of compilers use the CX register as a counter, counting down. So like, if we want to just have, we wanted to blast a row of pixels, you can do the repetition prefix for the S2SW instruction. So it'll keep on repeating it however many times you load it into the CX register. And I put one of my games on GitHub, and some MAME developer forked it and added some cool stuff. And this is one of the cool tricks that I gathered from him when I was looking at what he did with the code. Using that instruction, it just increments DI with the least amount of machine code, but that's all it really does is increments DI. And then this is a clever way to zero out the AH register, like in 1 byte. I mean, this shit matters too, because you have 512 bytes, so it's like, you don't want to just move 0 to like AX. That's like, I don't know, like 5 bytes or so, around, maybe not that many, maybe 3, but that's a lot. This is even less bytes than doing XOR AX with AX, so it's a pretty cool hack, I think.
It's actually 510 bytes because you have the 2-byte signature that takes up 2 of your bytes.
not to add all the overhead of setting up your video mode stack if you want it. I mean, when I say the stack's optional, I really mean it, because like maybe if you're really trying to save bytes and you don't need to do stack stuff, then kill those few instructions that do the stack. Next, talk about timing. Because for making games, you might want to like actually check timing for your ticks. There's a lot of different ways to do it. This is the way I do it. The memory location of 046C has a timer state. So I get it into VX, I increment VX by a certain amount, that's my amount of time. And it's like a fraction of a second. It's not like a super small amount of like milliseconds or microseconds. And then I set up a delay loop where I keep on checking VX, the extended, or like, the incremented version of VX to see when the clock state catches up to it. Once it does, it exits the loop. So that's like a cool little simple time delay loop. There's other ways to do it for quicker or like more granular time, but I like this one. It works pretty well for games in general. Now we're going to have a few slides on keyboard input, and I have my way of doing it. He has another way of doing it that might actually be better. This slide took a while to do. It's like several sprites. So this is optional. These are just directives or macros. I don't know. It's just saying every time I type left, it means 75. If I say up, it means 72. These are like the keyboard stand codes for left, right, up, and down. Being that you're going to have a game, these are key codes that you might want to have. And instead of like typing 75 or 77 or whatever, you can just type left, which just makes it easier. So it's definitely optional. It doesn't take up any extra space because this is an assembly itself. This is just a directive to the massive assembler. So this is kind of some code that I use as a template to get keyboard characters. I use the N16 BIOS call to get the keyboard state, and after that I clear the buffer and go to my next loop to start checking on which keys were pushed. Then the key state goes into AH, so I just compare AH with left, right, up, down, jump to whatever subroutine I want to do for whatever key was pressed. So the main loop for that is, if it was down, do that stuff, do the down stuff, do the left stuff, pretty simple for that. And then Brian here has a different, more sophisticated, better way of doing keyboard.
I wouldn't say it's more sophisticated. It's just what I did to get two-player input to work. There's probably a better way or more optimized way to do it, but this is the method I came up with. And so when the keyboard actually sends a key to the computer, it gets sent to an interrupt on the CPU, and that interrupt gets looked up into the interrupt vector table when you're in ring 0. And so the interrupt vector table says what chunk of code to execute when this interrupt happens. So keyboard interrupt is interrupt 9. Yeah. And then, so what I did was I overwrit the interrupt vector table with my own keyboard interrupt. So it's called an interrupt service routine. So anytime a keyboard button gets pressed, I take full control of what happens with that interrupt, and then I return back to the program. Alright, so this is the actual interrupt routine. I just push everything to the stack. NAL is saying into register AL, and 0x60 is the port that I'm reading from. And so that actually specifies the keyboard. So because this is keyboard interrupt, I get the scan code into AL, and then you now have the scan code. You can do anything you want with it, so you can actually reuse a lot of what Eric was doing, checking if it's a key value, is it up, down, left, right. In the snake game that I wrote, I actually do the WASD up, down, left, and right. And then for the end of it, you need to tell the, I forgot the name of it, but you need to send to the, I can't remember the name of it. Anyways, you need to tell the CPU that it's the end of an interrupt. And then you out, right, and then you return back. Sorry.
I forget where your code does.
Yeah. Let me practice this a few times.
Okay. So next we're going to talk about how to do random, because in games that's super important. If you're making your own game and you actually want it to be playable for yourself, you want to have some randomization in there. So this is just kind of like, I struck some slides with some visuals. This is some, we call it glitch harp, that my fiance Kurt Cocaine put together. It's on her GitHub. But what it does is it randomly fetches, with the random thing that we're going to talk about in a second, it randomly fetches data for what color, like foreground and background color to display. and then uses the heart character, which I think is like 0x02 maybe in the 437 code lookup, and then it just repeats that loop and just blasts a bunch of hearts to the screen. So it looks kind of glitchy, and it's a bunch of hearts, so instead of calling it glitch heart, it's glitch heart. So no, this is pretty cool visually. It's really easy to be able to do it. You just use the RDTSC instruction. It's the read timestamp counter. So it's a timestamp. I mean, that's all it really is. It's not really anything random. It's like the most pseudo-random you could have. But this timestamp is quick enough to where, I mean, you don't want to like, so the result goes into AX. You're probably not going to want to use the whole AX to count on for your randomization, because that would be a little bit slower. But the farther you get to the least significant bits, the more randomish they're going to look. So, like if you use AL or even the last nibble of AL by masking it out, you're going to have more randomish stuff to work with. And for the purposes of games and also what you saw with the hearts up there, the colors, I mean, there wasn't any super noticeable pattern, so it's good enough. Especially for a game. I mean, you're probably not going to be playing a game like Nibbles or whatever, and you know, a bad guy is going to come at you, like you may not be able to predict where the bad guy is going to go based on timing. And that's, I guess, kind of the point of how random you need it to be. So now we're into the second of three parts of this talk. Again, the last part being the demo is the cool part. But this part is going to be about debugging, like actually connecting GDB to QEMU, or the other way around. And this is, I think I avoid doing this because I hate GDB. I'm like an EDB user, like I like the Ollie interface. But when I have to, this is useful. But also, if anybody would ever be interested in the last demo that I'm going to go over, the boot me, crack me, the crack me kind of boot sector thing, this knowledge is kind of necessary. But we'll talk about debugging. So this is kind of like an outline of what we'll go over, like how to do OBJ dump with these things, and how to do GDB with QEMU. So this is pretty much it for OBJ dump. Just the syntax, the command to run on your image. You gotta tell it, you know, it's gonna. I mean, the D is for dumping. You gotta tell it's a binary. You're gonna say it's the i386 machine type, and then the address say 16-bit, and then your image. So whatever it says for your image, that's your name, obviously. And then for GDB, when you want to use GDB on your QEMU image, or your boot sector image, first of all, you just type GDB if you have it installed, and then just run this list of commands. Just type each one of these one by one. The only thing that you need to change is where it says your image on the first line, change that to your boot image. And this just sets everything up in a perfect environment for being able to use GDB as a debugger for your boot sector program. And I'll talk about some of these instructions in the next couple of slides. I kind of need this cheat sheet for myself because I still don't use GDB that often, so I kind of have to look at my own cheat sheet to know how to like even step or do a memory dump or any of those kind of things. I mean, I hate it. I can't stress this. I know there's like cool views you can do if you hack around with it, but like I hate the idea that if I want to know what's in a register, I have to type like a command to see what the registers are. Because sometimes when you're debugging, like you don't even know that you need to know what the register changed to until like in the debugger you'll see that it turned red. So why did that change? As opposed to this, like unless you actually ask what the register is, you're not even gonna know it. But anyway, single stepping is usually just step, but in this case you might have to type step I. If you want to step an arbitrary amount of instructions, it's step I and then whatever number. So step I 7 would be step over 7 instructions. There's really no good way to step over an interrupt that I know of. So when I get to like an int 10 or 16 or 13 or whatever, I just note what address I'm currently on, and I set a breakpoint for 2 bytes after it, because those instructions are 2 bytes. So that's how I step over those. And I'll talk about breakpoints and that kind of crap in the next slide. So breakpoints is just BR and then an asterisk and 0x, whatever address you want to go to. Then you just type CONT for continue to continue to that address that you set a breakpoint for. If you want to see the registers, it's info registers. If you want to do a memory or a stack dump, it's x/b and then whatever register you want to go to. And if you want to do a disassembly, it's disas or disas, and then the 2 addresses, like the start and the end address that you want to do a disassembly for. And you might ask, if I have OBJ dump, why would I do it this way? Well, sometimes OBJ dump doesn't disassemble it. like the alignment is bad, especially if as a programmer we're writing some really cool ass like self-modifying code, you know, this is going to be a problem. So to be able to live disassemble is really useful to do it while debugging it. So now this is the third part, the demo part. And yeah, I mentioned the self-modifying code. That's like another trick that I think we've all used just to shave down on like, even, I know I spent like maybe a half hour writing a super complex routine to do self-modifying code, and it only shaved off 1 byte, but that was the 1 byte I needed, so it's beautiful. But this is the game that I was inspired by from the POC or GTFO to Tranglix. So I'm going to close this slide and we'll see it running. See how bad I am at playing it. I mean, whatever, I'm going to stop playing it, but this Tetris, and actually, I think this version of it was not the original one that was included with POC or GTFO, because I think, I remember they had a discussion about the scoring system. They weren't even able to have a scoring system, like they couldn't figure out how to shave the bytes to even put a score in there, but I think they probably figured out some cool hacks, and now you got a cool scoring system up there. So that's that, and after I was inspired by that, I wanted to try to write my own game. So I wrote something that's kind of like a mix of Tron and Nibbles, so I call it Tron Solitaire because you're playing with yourself. And it's kind of like Nibbles, but the tail never disappears behind you, because I just thought that was kind of hard to implement. I was just too lazy to make the tail disappear. So I'll show you what this game looks like. And this is the one that main developer guy helped me out with. But this is the screen we're playing it on. You know, you can see the tail doesn't move behind it. If I touch my tail or the borders, I lose. And then you notice this little 2 thing down here. When I touch it, you'll notice the score in the bottom is going to change lower. It goes lower. So those red items will actually lower your score by like an order of magnitude, like whatever number shows up. That red one up there is an 8. If you see a green one, that'll actually multiply your score. And the point of these is you have to collect these power-ups in order to win. Because you can actually, if you get a high enough score, you will actually win the game. See how my score went up pretty significantly. I'm going to go catch this 3 up here, and right now it's like 5F. Now it's like A, it like went from 5 to A, which is pretty significant. And then another little, like I guess, Easter egg is if you get a red 7, that's like a poison 7 and you die, no matter what. But yeah, so in order, like, because normally, like, you'd think if I want to get the highest score, like, I'll play some super efficient algorithm to just fill up the screen. But if you just focus on that, you're not going to get a high enough score if you miss all the power-ups. So it forces you to kind of be, like, chaotic, where you move your snake, so it actually makes it harder, because that's just the design, which is kind of cool. And, I don't know, I think this kind of thing is just really neat, like, this kind of emerging behavior, just 512 bytes of code, or less, and then I'll die. And it used to just flash like you're dead or something, I forgot about that, but he did a fork of it, maybe, so it just resets the game when you die, which I think is kind of a better implementation. So now it's for his game. I'm going to actually, so when you close this,
yeah,
click into it, and then we'll, fingers on keyboard.
Yeah, so this is a 2-player game that I created. Basically, it's kind of like a mix of Snake, Tron, and yeah, you just kill the other player. Don't hit the walls. You have a starting seed, but you'll see if you go back and hit that, your tail will turn into a wall. So if the other player hits your tail, or is getting close to your tail, if you can like hit the seed, you can close it, and you can make them die and not kill you. So we'll play.
Yeah. Okay. Finding stuff. All right. And yeah, this restarts after somebody loses or wins too. This one, this is just to show the GitHub page for it. It's a solitaire game. It's text mode, so it's not like super graphical. Unfortunately, for whatever reason, on QME1 OS X won't load it, so this is just for reference. So like this is it trying to load it, but it doesn't, whatever. There's like a couple demos. There's one other demo I can't run, but the rest work fine. This one's just kind of visual. The project, they call it Nyan Boot, or however you say that. I'm not an expert on memes. But this thing, right? So that's pretty cool. And are there any kids here? Okay, good. So this project, it wasn't mine, and then Average Joe down here pointed this out to me. I think he like tweeted it to me or something like that. Like, check this out, you might like this. And so then, of course, I liked it, and then I forked it, and I modified the colors because it was just yellow. So I can officially say I contributed to something where I forked a butt and made it red. This is another one that doesn't load, which is okay. I think there's two more. So this is just, it's not a game, it's not a program, it's just like a visual, just to show kind of, I guess, like a simple, cool thing you can do in graphics mode. So again, this is just a 512 byte boot sector that's using graphics mode. And I think they even had enough bytes to throw a little copyright down there with their name. I mean, they had enough space to do that, that's kind of cool. And then for the very last demo, this is actually also kind of, I think technically it's a Quinn, which is a program that displays itself. This is the Boot Me Crack Me game. This is just one level of the game. On my website, xlogicx.net, there's like a tab at the top called Boot Me Crack Me if you want to see the other levels. But I'll walk through the gameplay of this level, which is called Tutorial. This game only has like two functions. One of them is to do a dump of itself. So it dumps itself as hex onto the screen. And then there's another option to input just one byte. So you do input, you type your byte, your hex byte, and the program does whatever it decides to do with it, and it's up to you to figure out what it did with that byte, and what's the significance of it, and what byte you really need to put in there to win the game. So I'll show you the dumping. This is the program, one of the levels, I guess, like it. So like you could disassemble this. In fact, you could use the OBJ dump and disassemble it that way too. So notice, I guess, look towards the end, like right where the null start. It's like the 1301 or whatever, if it's even visible from where everybody's sitting. And I'm going to go back to this, and then I type I for input mode, and I'm just going to type like 88 and enter that, and then I'm going to dump again. And now you'll see the 1301000888. You'll see the 88 show up. So what's happening is whatever byte that I typed in, it puts that byte right there. So now it's also self-modifying code. Like, in this case, not necessarily, but some of the levels, the byte you're putting in there could be an instruction, and whatever byte you put in there, it's executing that. And it's up to you to change the execution flow to get to the point where you win the game. Some of them are that complicated, but in this case, it's a little bit simpler. I'll just do one more. So this was 88 just to show this is pretty consistent. I'm going to do FF and dump it, and we should see it, we see it FF in that same location towards the end. So I'm not going to dump it on screen right now, but if I were to do an OBJ dump, or before I get to that, if I were to count the bytes, the address that this byte is located at is in hex 167 bytes into the program. So hex 0x0167. Being that the 07C0, or yeah, 07, whatever, it's 7C00, yeah, 7C00. There's an instruction if you disassemble it where it's doing a compare against the address of 7D67, so that's actually the 167 plus the 7C00. So you'll see it comparing against that pointer for whatever reason. And the byte that it's comparing against is in hex 42. And if it's not 42, it doesn't do the thing, it just repeats. But if it is, it does something else. So that's the idea. You're supposed to reverse it to find that instruction. So I'll go back and I'll do input and I'll type 42, which was what it was looking for.
The answer.
And that's how you win. So this is the simplest crack me. And I think there's like 6 or 7 levels. Some of them, I mean, to give a couple of spoilers, like I said, control flow is for a couple of them. Sometimes the bits get shifted or rotated. Sometimes even the timing that you change it matters. Like it'll check the clock, and you might put in the right input just at the wrong time. So some of them get a little bit more complicated. But this is a fun way to waste a lot of time with just 512 bytes at a time. So this is where either of us could take questions, I suppose. A lot of time. Yeah, we finish early, whatever. I know it's obscure, so if there's no questions, that's okay, or you can ask afterwards. Yeah, you.
You talked about how you had to write your own keyboard intro handling routine for 2 players. Can you talk about why you had to do that?
Repeat the question.
So the question is why did I write a keyboard interrupt to handle 2-player input? And I didn't necessarily have to. The keyboard actually stores a buffer, and I probably could have looped through the buffer, but I wanted to, going through this project and building this stuff is a learning experience as well, so I just wanted to learn how to interact with the keyboard. I thought it was cool and wanted to share it.
Yep. I would just add a tangent to that. Like this whole thing, I think for both of us the point was it was a learning experience. I think, for me personally, I think the best way to learn a programming language is to write games because it forces you to pretty much use every important part of a programming language, and it's also interesting to play around with. Like in fact, when I learned the propeller microcontroller, the first thing that I got wasn't the propeller chip or propeller dev board. I bought this thing called the Hydra, which is like a video game system based around the propeller chip. I figured if I want to learn propeller and propeller assembly, the best way to learn it would be to program games on it, which turned out to be mostly true. In fact, I learned a lot of stuff that were takeaways for what I even implemented in this project, namely the way to implement sprites. I was actually kind of shocked to, like a couple weeks ago, pick that book back up and look how they're implementing sprites. And it was literally doing 8x8 4-color sprites. I'm like, holy shit, this is like, maybe I didn't reinvent this. I mean, obviously I didn't reinvent it, but the fact that the colors and the amount of pixels was completely the exact same what I ended up doing is kind of funny. But yeah, for us, I mean, we're not doing this like pros. This is, just for us to learn. And I guess, if you really wanted to experiment around with the ring 0 instructions, like there's the driver way to do it seems too complicated, so that's why I went with this route. And unfortunately, I learned that, like I said, those instructions weren't as interesting as I wanted them to be. But yeah, it was all learning.
Is there any more questions?
Kind of side with this, you guys ever messed with firmware before?
I personally haven't, but I'll let Eric speak to that.
I mean, no, not technically. The closest I would have got was when I was in school. I mean, this is definitely not firmware, but they weren't even FPGAs. They were PLDs, we call them. But so that's not actually. It's hardly even firmware in the sense that it's still kind of like hardware, like VHDL and that kind of stuff. But that, I guess my answer is that's the closest I got with it. And I thought that was incredibly fun because of how low level it is. I say this a lot, but I always think whatever I'm working on is too high level for me. Like even recently at DEF CON, I gave a talk called Assembly Language is Too High Level. And the whole talk was about writing software in machine code and all of the cool things you can do with machine code that you actually can't do with assembly, which is amazing. And there's a lot of things. It's not like simple, obscure things. There's a lot of stuff you can do in machine code that assembly doesn't allow you to do. So when it comes to like FPGAs and PLDs, that's like a couple layers of abstraction lower because I mean I guess one lower than machine code is microcode, but I mean anything I can actually play with myself I'm not interested in because Intel keeps that locked up. But FPGAs are great, and with the propeller chip, you can actually write your own. Like you can rewrite the processor. They open source the code for a propeller, so you can actually load your own propeller implementation on an FPGA. Which is why I like when Arduino said they're open source hardware, like, okay, kind of, but until I can poke at the Atmel chip, no, you're not really completely open source. I mean, and all the while, yeah, to be fair, propeller didn't do that until like way, way later, but still, that's the closest to firmware I've ever touched.
So most people don't know or use Propeller, so I'm kind of actually curious, do you find yourself mostly working in Propeller itself, or do you work with Spin, or do you work with some of like the really interesting bytecode stuff that they actually load onto those?
It's a good question. Repeat it. It's talking about the propeller and if, like what environment that I typically like. If I use their high-level language called Spin, which looks a lot like Python kind of,
Yeah.
or whether it's that or assembly. And so I started with Spin. I ended up having to go to assembly for what I was writing. I had this bass guitar that I put a propeller in, so I could do synthesis with. But it doesn't have a lot of hardware for like audio or all the cool bells and whistles. You're supposed to program it yourself. So I had to write an audio driver, and the spin was just not gonna be, not fast enough. So I had to do that in assembly, and that was like one of the hardest fucking things I've ever done. At the time, like, you know, and looking back at the code, I'm like, okay, that wasn't too bad, but it was, debugging is hard. Like, how am I gonna go, this doesn't sound exactly like a sine wave. I had, like, my debugger was no scope. You know? But that's, so assembly was, I used that probably more than I used spin. And as far as the relationship between machine code and assembly, I've loved looking, because I looked, and to compare, it's like on the other side of the spectrum. When you look at Intel, like assembly and machine code, it's like so much, like, there's a lot of differences. It's not one-to-one is the best way to put it. Whereas Propeller, it's nearly one-to-one. And then, like, the two exceptions I found where it wasn't, it kind of, in my opinion, didn't even count as being an exception. It was still, I'd say it's almost 100% one-to-one, which is pretty beautiful. The language itself is like, especially when you look at the machine code, like, every instruction is the same amount of bytes, which is amazing if you look at x86. There's no stack, although you use kind of like the whole memory is like stack and registers. It's really weird. There's no interrupts. It's a cool architecture.
It's pretty sweet.
Glad somebody else likes it. It's much really about that. Yeah. Cool. All right, I think we're done.